Now we're going to look at how we can evaluate our simple linear regression models. So we're at this phase in the modeling process, the fourth step, and we have solutions. We now know how to find our best slope and our best intercept for a given set of data if we're trying to fit a linear model. But then we'd like some metrics to use to decide if that model's good enough or if we need to keep working on it, adding some other features, for example. And this idea of evaluating model performance will also be helpful when we're trying to compare and choose between two different models. So to see some ways to determine if this is a good fit, we're actually going to jump back to the notebook so we can visualize this, and then I'll summarize the results we see in the notebook on this slide. So we are still in the simple linear regression notebook, and this is where we left off. This was our model and our data points. So in this case, visualizing these two is very important as part of your model evaluation, because you want to make sure you don't have some crazy outliers that might be, controlling the model. But the next things that we're going to look at here is what's called the root mean squared error, because our mean squared error that we'd been minimizing before was in units inches squared, or y squared, which is a little hard to interpret. And so taking the square root of that's a common way to get it back into units where we can easily interpret. So this says on average, I'm off by about 3.3 inches in this model. And ideally you want to try to get that RMSE as low as possible, especially if you're choosing between two different models. But that's not the only piece of information we want to consider. So the next piece of information, I'm actually going to draw up here and then we'll calculate it. I want you to notice that we can look at the variance of our original y values. So if you imagine taking every single data point here and just like projecting it onto the y-axis and then getting the variance of that data, it gives us a sense of the spread of all the children's heights. Separately, we could look at the variance from the model. So if we take at each data point that we have here, if instead we look at the predicted child's height, right, and we start compiling that histogram of data, we would also have a separate variance, right? The variance for our predicted values. And ultimately, the ratio of those two variances give me a sense of how much variation did the model actually capture, right? There was a lot of variation in this original data set, which we can see here. I'm just showing the range, not necessarily the variance, but you can imagine the variance is pretty big here, and then my variance is smaller here. And so that ratio of variances is a useful metric for us in deciding how good the model is explaining the variation that we see. The closer that ratio is to 1, the more the model's capturing the variation that we see in the data. And it turns out that that is completely related. Oops. And it turns out that that whole concept of capturing that ratio of variances is exactly something we can get from the correlation coefficient, at least for simple linear regression models. And so it's basically the mathematical reasoning where I told you when I introduced correlation that the closer the correlation was to 1, the more clustered around a line the data points are. And the further it is from 1, the closer it is to 0, the more spread out around a line they are. Well, that's actually, you can prove that because of this ratio of variances. So if I just calculate, and this is not a proof, I'm just going to show you mathematically how these are equivalent. If I calculate the ratio of the variances in my prediction, the y hat, to the variances in the original model, I get 0.103. That's exactly equal to my correlation squared. So correlation squared is a useful metric in helping us understand the proportion of variance in the data that the model explains. Typically, we want that to be as close to 1 as possible, but sometimes just depending on the data, right? Especially when you're talking about human data like this, you're not going to get a model here where you have an R squared close to 1. There's just so much variation in what happens in humans that you're probably going to be okay with your R squared there, only 10%. That's more realistic for this type of data. But if you were comparing between two models, using that R squared can be a helpful metric because ideally you'd want to take the model that's going to capture more variation or that has a higher R-squared. All right, the next thing that you're going to use to help you visualize how well the model's doing is actually to plot the residuals. So those were those errors versus you can either choose your input predictor. So in this case, the average parent height, or you can choose the predicted output. So I also am going to plot this exact same thing with the predicted Y. And I'm showing you both because in here you're going to notice the picture looks the same. It's fine. It's just that my label here has changed and some of my units right here have changed. But basically, if you flip back and forth, I can zoom out so you can see this better. Right. Okay. So that's not an accident. They look the same. The point is that what I'm looking for as I go from left to right in these plots is I want to just see that there's no pattern in the data. I want to just see that roughly it looks basically randomly spread and that there's not a real wide change in its spread here. Like it's not fanning out or funneling in. In general, if I have residuals that look like that, it's a way for me to see that my model itself is doing a good job of capturing what's happening equally in the data. So I'm like equally kind of right going around through the middle of these points here. I'm not like under predicting a ton for small values and over predicting a ton for large values. It's saying, yeah, that's a linear model. It's doing a good job of capturing the trend in your data. And you're seeing that because your residuals look pretty randomly spread. They're going to be, their average of your residuals will always be 0. So all these data points will average out to 0, but we're going to see that sometimes you get some interesting trends in your residuals. If that's the case, that's usually an indication that you need a different type of model, that a linear model is not capturing the behavior. Maybe you need a quadratic or another type of model. And we're going to follow up on that in a future video. So these are the key things we're looking for. Let me go back to the slides now and we'll look at this. I'm going to point out also that this plot of the data versus the model works great when I only have one feature, right, that I'm using to predict my outcome. When I have more than 2 features, it's no longer possible to even visualize it. And it gets tricky to visualize in 3D when you're using 2 features. So I would say in general, that's where this idea of using your predicted output versus your residuals, this is going to become really useful for us when we start having more than just one predictor. Let's head back to the slide. So now to just summarize what we showed, common metrics we'll be using to evaluate our models include the RMSE, as well as the correlation coefficient squared, which is going to capture this proportion of variance that the model is explaining. And then visually, we're going to be looking at residual plots and looking ideally for no patterns and a similar vertical spread. So here are the results for the Galton data that we just did in the notebook. And together, putting all this together, this tells us that a linear model is reasonable. We don't need to continue like transforming the variables or doing anything else. It may be useful, right, to get more than just one predictor, because currently our R-squared is not that close to 1. And it's quite possible if we added in more than one predictor that we'll be able to get our RMSE even smaller. So this is telling us we're on the right track, but we could keep going, especially depending on the level of accuracy we want in our model. In general, here's an example of 3 different residual plots. I'm plotting them versus these 2 are versus their input values, x. This one's versus the fitted values, y prime. Like I told you, in the case of simple linear regression, it's going to look the same whether you use your predictor or your y hat. But in general, as we start moving towards more than one predictor, rather than having to make a bunch of these, we're going to just stick with this version of the residual plot because we can quickly look at it. So this first one on the left, this looks good. There's no pattern. I have even spread. This is indicating that this simple linear regression model is a good fit. The second one I have, so even though the average of these data points is 0, this is saying, no, there's definitely a pattern in this data set, and it's hinting you should try a transformation of the data before you try to fit a model. And so we'll look at that in an upcoming video, how we can transform. And this last one, so I don't see so much a pattern, but what I am noticing is some uneven width of, or like variance in our data here. Like I'd say it's kind of, for the most part, I'm doing that, and then it's going like that. And this one's kind of really spreading out here. So I don't have equally accurate regression estimates across my range of my predictor value or my predictor variable. And the other thing that's a little bit strange about this one is like most of my residuals in the negative direction are all within, you know, a distance of about -5. But then I have a much bigger spread above in the positive direction. That's also something we want to watch out for, because again, it's just saying you probably can improve on this model. All right, so let's think about this in a little bit more detail. Suppose I tell you you have two data sets and they both have, okay, these data sets A and B are both pairs of data. So they both have X and Y data points. Each of these have the same mean values for X, the same mean values for Y, same standard deviation of X, same standard deviation of Y, and the same correlation. And so these are the actual values for these two data sets. So my question is, does this mean both data sets must be the same? So if I were to plot, for example, a scatter plot of A versus a scatter plot of B, am I going to have the exact same scatter plot? I'm not going to be able to recreate that, but am I going to have that exact same scatter plot? Or is it possible they could look different? And then the second question is, do they both have to have the same regression line or not? So take a minute and let's talk about it. So the answer to A is false. We're about to see some examples in the notebook, but I can give you some toy data sets that have all of these same statistics, but actually look different. But for B, the answer is true, because the regression line, remember, it just depends on your slope and your intercept, and your slope and intercepts are completely determined by these statistics. So they will both have the same regression line, even though the data sets will look different. Let's go to the notebook and see how this can happen. So we're still in this simple linear regression notebook, and now we are going to jump to evaluating and comparing linear models. And so this part of the notebook has a bunch of built-in functions at the top. We've defined a lot of them already, but this is just so it's all in one place, because we'll be calling these throughout this demo. And then this next line is just to get some of the styling in the pictures the same. But here I'm going to show us 4 different data sets. And I'm going to point out that in each data set, they all have the exact same least squares regression line. There's my intercept of 3, my slope of 0.5. And in fact, all of them have the exact same statistics for the mean, standard deviations, correlations. You can see them all here. This was for all 4 data sets. However, only when you visualize them can we see how this model doesn't make sense in most of their cases. So let's look at, there's data set 1 versus data set 2 versus data set 3 versus data set 4. Okay, so visually I can see here that at least using the least squares regression fit, the only data set that makes sense for is this one. This one we're going to see in a minute. If I get rid of this outlier, or if I somehow just don't model it, then I can get a line here, but it's not going to be the least squares regression line using all of the data, including the outlier, which we'll see in a minute, because I'm going to plot the residuals first. So one way, like I said, visualizing whether or not you have a good fit, one way to do that is looking at the actual original data, like we are here. But as we add more and more features, that becomes tricky. And so looking at your residuals becomes very informative. This is the residual for the first one, and that's randomly scattered, evenly spread. This one looks good. The residual for the second one shows a pattern, which is telling us, yeah, that's definitely not going to be best fit by a line. And we can see that. What would be much better here is to do this type of quadratic. The third one, so look at the third one. So your residuals have this crazy linear pattern and then the random one that's way off here. So again, that's telling you, okay, maybe a line would be good, but you're gonna have to take care of this outlier first. And then the last one is my residuals all look like this, and then I have this crazy situation, or my data point all looks like that. Excuse me, here's my data. My data looks like this, and I have this crazy situation, and you can see that happen because my residuals are like, something crazy is happening here. So the takeaway is that you should always visualize these before fitting any models. And again, the only one where straight out of the box, the least squares simple linear regression model makes sense here is this first one. But I would only know that by visualizing, because otherwise their statistics and their least squares regression fit were exactly the same. So to summarize what we were just doing in the notebook, ideally, when you're evaluating your model, you'll be visualizing the original data, computing key statistics, looking for outliers or anomalies, and then doing your performance metrics. And so for our simple linear least squares model, we're using RMSE as well as the correlation squared, and then visualizing the residuals. And we want to emphasize that sometimes people get overly hung up on performance metrics, but it's really important to include the visualization as well. So the 4 data sets we looked at actually are a famous set of data. They're called Anscombe's quartet. And we can see visually, here are the least squares regression lines for these 4 data sets, and it's the exact same line in each case, but really only the top left data set does that particular model or that particular line make sense for. So it's a big takeaway before modeling. You should always visualize your data first. And sometimes it's hard to see patterns or trends in the actual data set itself, but usually residuals will help you spot if your model is not doing a good job. If you could, for example, have maybe made some transformations or chosen a different model. So this is our starting point for evaluating models. And as our models get more complicated, we'll add in a few other recommendations. But in general, these will be common practices in our class for choosing and evaluating models.